Alrighty, elements. I see 15 of you are already logged in, and I am here basically today to answer any questions that you have after studying for Big Idea 2 test. It could be from Unit 4, Unit 5, Unit 6, any concepts, any specific question, you can let me know. Alrighty. I guess I'm going to wait for your questions. How you guys feeling? You feeling ready? How did you find the practice test? Sure, Eric. Lattice Energy. So the technical definition of lattice energy is amount of energy released when 1 mole of ions in gaseous state combine, or when ions in gaseous state combine to form 1 mole of an ionic compound. And its equation for NaCl will look like this. Na plus in gaseous state plus Cl minus in gaseous state gives you NaCl solid. For us, the implication of lattice energy is in figuring out the strength of ionic bonds or ionic compounds, and kind of predicting the melting and boiling points, because the stronger the ionic bond, the more energy it will require to break it. And lattice energy's measure is given by Coulomb's law. So lattice energy is proportional to the charges on the ions and inversely proportional to square of the distance between them. And you had a few questions where both charge and the atomic radius was changing, and then you guys were confused. So charge is a bigger factor than the ionic radius because these ions are very, very small. So little difference in ionic size doesn't make that much of a difference as the charge does. But if the two charges are the same, then the ionic radius will play a role. Is that good, Eric? Sarah, could you give an explanation on the connection between polarity and IMFs? Okay, so Sarah's question around polarity and IMFs. So IMFs are a very broad term, a generalized term. And one type of IMFs are dipole interactions, and other type of IMFs are hydrogen bonds out of very many others. These are the two, and both of these happens because of a polar covalent bond. And in case of hydrogen bond, this polar covalent bond is formed between hydrogen O or N or F. And when that happens, that there is a polar covalent bond between hydrogen and one of these, then the intermolecular bond is called hydrogen bond. And dipole is you have a polar molecule HCl, and what's going to happen is, because Cl is a highly electronegative atom, then electron cloud on Cl minus, the shared pair stays more towards Cl side than H side. As a result, H acquires a positive charge, Cl acquires a negative charge, and the opposite ends attract. So this side will attract this, and this is dipole-dipole interaction. And both of these happen because of polarity. Alloys and conductivity. Okay. Alloys. Alloys are metal solutions, meaning when you take a metal and melt another metal with it, then that is an alloy. And alloys can be of two types. One are substitutional alloys, and the other ones are interstitial alloys. And substitutional alloys have same size atom of two metals. So one of the atom or more of the atoms can be replaced because the atomic radii are about the same. And as a result of substitutional alloys, the flexibility or malleability kind of remain the same. But interstitial alloys are formed when the two combining metals have sizable difference between their atomic radii, and the smaller metal atoms kind of go and sit in between. And because they go and sit in the interstitial spaces, they restrict the movement of atoms and makes the alloy more rigid. So interstitial alloys will tend to be more rigid than substitutional alloys. I have to go back on the chat. So I answered Sarah's question, Ellen's question, Ethan's question. Could you review the types of para, dia, and ferro? So Ethan, ferromagnets are permanent magnets, meaning that they will have quite a lot of unpaired electrons, and whether you apply a magnetic field or not, they will be acting as magnets. These are permanent magnets, like the ones that you put on your refrigerator. They are always magnetic. And a lot of iron and its alloys are ferromagnets. Now, in terms of para and diamagnetism, diamagnetic substances do not exhibit magnetism in an external magnetic field. And paramagnetic substances do. And the result of that is, guys, a lot of the motors in today's world, so many things are run by motors. A lot of the motors and a lot of the things that you see when you turn on a light, right? Generally, when the current flows, then this substance starts acting as a magnet. And when you turn off the switch, then this substance stops acting as a magnet. So this property is what we use a lot these days. That is why it's an important topic. And a paramagnetic substance at molecular level will have unpaired electrons, one or more. And the more the unpaired electrons, the greater the paramagnetism. Diamagnetic substances have no unpaired electrons. And one other connection that we had, so you can figure out whether it's para or dia by drawing orbital diagram. The other connection we had is we always thought oxygen was diamagnetic, but in laboratory, scientists observed that oxygen acts paramagnetic, and that led to them coming up with MO theory. So that is para and diamagnetism. Next question is Eric's. If a question asks for the shape, is it molecular geometry, electron domain? So if it is asking for shape, it is generally molecular geometry, not electron domain. Harshita, can you please do 18 on the Lewis structure via CPI hybrid? Harshita, you'll have to work with me. I don't have my packets with me today. I just came home. Actually, I was at the district office for a meeting. So can you please type the question or tell me the context? I'll be happy to do Harshita. That was Harshita R. Harshita M. Go over molecular orbital theory. Okay, come in your way. MO theory. So MO theory says that atomic orbitals, AO atomic orbitals, combine to form molecular orbitals during a covalent bond formation. And it says when atomic orbitals combine to form MO, the molecular orbitals are of two types. They are either, actually I should write anti-bonding on top. They are either anti-bonding molecular orbitals or they are bonding molecular orbitals. If they are bonding molecular orbitals, then they have lower energy as compared to the atomic orbitals. So electrons tend to fill the bonding MOs first because electrons tend to be in the lowest energy state. Anti-bonding MOs are higher energy orbitals, and electrons tend to go here later. One thing that molecular orbital theory explains very well is paramagnetism of oxygen. And using MO, you can figure out bond order, which is number of electrons in bonding orbitals minus number of electrons in anti-bonding divided by 2. And if a bond order comes out positive or greater than 0, then you know that it is the molecule will form. Also, the numerical number of bond order tells you how many bonds will be there. Now, what happens in MO theory is they will give you, at our level, they'll give you the diagram. For example, atom 1's 1s orbital, atom 2's 1s orbital, they'll combine to form molecular orbital. So these ones in blue, I'm just drawing it color-coded so you can differentiate between MO, molecular orbitals, and atomic orbitals. So when atomic orbitals combine, they formed one as sigma 1s and sigma asterisk 1s. So anti-bonding 1s, and on the energy axis, you can see that anti-bonding has higher energy and bonding has lower energy. So these diagrams will always be given to you. You just keep filling. Just remember, if you have sigma 2p and you have pi 2px and pi 2py, I'm drawing the other one for fluorine, nitrogen, where they are higher, otherwise they are lower. This sequence is flipped. Remember, if they are same energy orbitals, these two are same energy, right? They are on the same place on the energy continuum. Then you do not pair them up. You first put single, then you pair it. You can pair here because there is only one orbital, but if they are two of the same energy, then you do not pair them. So that is Harshita's question. Eric. Eric Wong. Also for VSEPR models, is it just molecular or is it? No, it is both. So you need to know electron domain geometry. And if there is a molecule that does not have lone pair on the central atom, then electron domain and molecular are both one and the same thing. But if there are lone pairs on the central atom, then it is the molecular geometry is different than electron domain, and in that case you do need to know both of them. Eric. Alicia's question, can you explain why between H2S and BCl3 H2S has a dipole moment? Okay, so between H2S and BCl3, if you draw the structure of H2S using Lewis structure, the steps, it comes out to be this, and BCl3. BCl boron is one of the exception, which is happy with 6 electrons, so there are no lone pairs on the central atom. So if you look at the dipole of BCl3, it's a symmetrical molecule, right? And all of the dipoles will cancel each other out because it's a symmetrical molecule. So net dipole here is 0. But because of the lone pair on H2S, it actually is like water molecule. Two lone pairs. Remember, lone pairs repel each other greatest and repel the bond pair more. So this angle gets scrunched, and this angle is 105 degrees. That's a side that doesn't relate to this. But because of this bent shape, the dipole moments, individual dipole moments, do not cancel each other out. And that is why this is polar and that is non-polar. Dissolution. So dissolution has 3 steps. In dissolution, you have a solute and you have a solvent. So solute particles will have some interaction between them, right? Depending upon their nature. Solvent particles will have some interaction between them depending upon their nature. So step 1 or delta H1 is separating out these particles. And to separate them out is to work against their intermolecular force. So H1 is always positive. Second step is you separate out the solvent particles. And again, you're going against the IMFs here. So you will be giving it energy. So now that the solute and solvent are separated, then you mix them together. When you mix them, one or the other thing can happen. One thing that can happen is solute and solvent really like each other and they mix really well with each other. There's a lot of attractive force. In this case, delta H3 will be negative because energy is released. The other thing that can happen is solute and solvent do not like each other much. They're not very close to each other. In this case, delta H3 will either be positive or slightly negative. If this is the case, then the overall delta H ends up being positive and the reaction is endothermic or feels cold to touch. And if this case happens where delta H1, H2 positive but H2 negative, in this case, it is an exothermic reaction or heat is given out or the overall reaction feels warm to touch. Catherine, how would you know if a molecule Lewis structure has a resonance? You have to calculate the formal charge for each of them. So, Catherine, that's the long way. If you calculate the formal charge for each of the molecules, it will take you very long time. One shortcut is a traveling double bond. Like in carbonate or SO3, you can see that this double bond can easily travel, right? If you look at N double bond O single bond O, now this can easily travel as well, right? Where there won't be a resonance like COOH, CH3, right? This double bond cannot travel here. You know why? Because there are 2 lone pairs on it already. There is no place for it to travel. So this one will not show resonance, but this one will show resonance. But if you truly wanted to evaluate the structure, then the formal charge is the way to go. So Shravya, please type the questions because I don't have my sheet with me. Hybridization. So hybridization refers to how many electron domains do you have around the central atom, and then you align the hybridization with that. Remember, hybridization occurs only on the central atom. As the side atoms approach the central atom, its S and P and D orbitals undergo change or hybridize to make room for the incoming atoms. That's called hybridization. Now, as we say electron domain, we may mean 3 things. We may mean a bond, we may mean a lone pair, we may mean a single or a double or a triple bond. All of these are just one electron domain. So here, if we were to look at carbonate, this is the central atom. There are 3 electron domains. Even though this is a double bond, it's 1 electron domain, 2 and 3. So now you got to see, for 3, you need 3 orbitals mixing, so it will be sp2 hybridization. If there were 4 electron domains, it will be sp3, 2 is sp. Okay, you're welcome, Ethan. Kelton, no, there will not be a Lewis structure where lone electrons are not in pairs. That is called odd electron species. They have been phased out from AP exam. Harshita, AgNO3 melting point at 212 sucrose, melting point. Why does this happen? Okay, so AgNO3 has 212. Sucrose is 185 and sodium is 99. So basically, they are leading you to the type of bonding. So if you look at sucrose, C12H22O11, you know it's a non-polar molecule. So between sucrose molecules, they will be LDF. So when you're melting sucrose, you're melting LDFs. Sodium metal by itself has electron C model, right? You know this, right? So this is sodium metal, and silver nitrate, which is Ag plus NO3 minus, Ag plus NO3 minus. This is an ionic solid. So ionic solid will have the highest melting point because ion-ion attractions are pretty strong and they keep the ions together. Then electron C model will be next higher. No. Well, it should be. So metals kind of vary and there's only 1 electron. So attraction is not that much. So this is shown to be lowest. If it is lowest, you'll say there is attraction, but because of delocalization of electron in this model, it's not that strong. And sucrose is shown to have fairly high, even though it is LDFs. Sucrose is a very large molecule with a large surface area. So its LDFs are significant, hence its melting point is higher than that of sodium metal. So really you have to explain it based upon chemical bonding. Okay, Harshita got it. You're welcome, guys. Real versus ideal gas deviations, okay? Real versus ideal gas. So in ideal gas, we make 2 assumptions. One assumption is as the gas particles are hitting the wall of the container, there is no intermolecular forces. But in real life, there are intermolecular forces which reduce the force that the molecule hits the wall with. As a result, in real gases, the gas pressure is lesser than ideal gas. And the second assumption that is made is that the gas molecules are far apart and the volume that they occupy, this is the total gas. The KMT says that most of the space is empty. So if you were to compare the gas particles volume to overall volume, then it is a very, very, very small fraction of the overall volume. So gas particles have negligible volume, but the fact is that in real life, the gas particles do not have negligible volume. So what ends up happening is if you include this volume, then the gas volume is actually larger by this one. So real gases have higher volume. That's why to make real gases behave more like ideal, you subtract a quantity from the volume, and to make real gases behave more like ideal in terms of pressure, you add it. And this effect is more pronounced at high pressure. The deviation is greater at high pressure and low temperature. At high pressure, what's going to happen? All of these will be scrunched together. As the molecules get scrunched together at high pressure, the overall volume is lower. 2 things are happening. A, the IMFs are increasing. B, the volume of the gas particle as compared to the overall volume becomes significant because overall volume is lesser. And at low temperature, what happens is because the particles move slower, you know, the average kinetic energy is directly proportional to temperature. So the IMFs between them become not negligible, they are significant. And that is why deviation is greatest at those points. Okay. How do you determine Eric's question? If a substance is more soluble, do you consider the energy required? So solubility, Eric, you got to look at case by case basis. So the basic concept is light dissolves light. So you look for polar solute and polar solvent. So if it is KCl, you know, it's an ionic compound, it will be soluble in water and not soluble in CCl4. Now, I wonder if you are referring to that one problem where they had an organic molecule like CH3OH, CH3, CH2OH, and CH3, CH2, CH2OH. If you are referring to that, there was a different criteria here. Solubility will mean these molecules will have to go arrange themselves around K and Cl, right? So if this O, that is the negative charge, has to be attracted by K, the smaller the molecule, the easier it is to align it. So in this case, the smallest molecule had the highest solubility in KCl. But the concept is light dissolves light. So if it is a polar substance, it will dissolve in water and polar solvents. What is the purpose of finding bond? Bond order helps you ultimately determine what is the structure of the molecule, how many bonds are present between any two elements in a molecule, and bond order helps us with the knowledge that yes, this molecule can form, and yes or no, this molecule cannot form. And if the molecule can form, then between the two elements, how many bonds are present? Okay, welcome, Akshay. So what happens, Akshay? In MO theory, there are two ways. Generally, the sigma, 2p sigma, is lower energy because sigma has a greater overlap versus pi that are overlapping top and bottom. But it sort of undergoes hybridization between sigma and pi. So sometimes the 2p sigma orbital takes some energy from the pi orbitals and jumps higher in energy. It's sort of hybridization. It's more experimental observation. And that's why they've come up with two different skeleton for MO theory that you have to follow. Okay. You're welcome, Harshita. Shunali, could you go over 21 on the chapter? Which is more likely to exist, Shunali? So I don't have the diagram here, but basically you fill in electrons. So in the first one, right, is like that. Second will be like this. And third is 1s2, 2s2, 2p. So there are three. And there are three in atomic. So here there are two, and then one, and then one, and then two, correct? So tell me which molecule they're talking about, Shunali. I don't remember which molecule it is, but let's say if it was nitrogen. Okay, so nitrogen has 7 electrons. So 1, 2, 3, 4, 5, 6, 7. And 1, 2, 3, 4, 5, 6, 7. I'm drawing the atoms, right? This is atom 1's electrons. This is atom 2's electron. Now let's start putting them. There'll be 2 here, right? 1 from here, 1 from here. There will be 2 here. There will be 2 here. There will be 2 here, and this for single, and then they get paired, and then single and paired, right? That's it. Now our electrons run out. So to figure out if N2 will form, you count all the electrons in bonding orbitals. Bonding are the lower energy one. This is bonding, this is bonding. These are all bonding. So if we count electrons in that, that's 2, 4, 6, 8, 10. 10 electrons in bonding minus how many in anti-bonding? 1, 2. So 2 and 2, 4 divided by 2, that gets you bond order of 3. Meaning yes, and 2 is possible, and there'll be 3 bonds between 2 nitrogen. So that's how you use this information, Shunali. Eric's question, if it was 4 different kinds of ionic compounds and asking the ranking, how would you approach such a problem? Eric, actually, that reminds me, somebody, I forget who, maybe it was you who said, can you please do number 1 from the retake quiz today, which had like Al2, S3, I tend to say, and then SrCl2, and A2O, and maybe let's say KCl, I forgot which was the 4th one. And it asked you, I'll answer your question, but I want to answer this first. And it said, rank them in order of melting point highest to lowest or whatever. We know this one will have highest melting point because the charges are 2, 3, and 2. Now this will be lowest because charges are 1 and 1. Here charges 1 and 2 and 1 and 2, right? 2 and 1 and 1 and 2. So the charges are similar. So you go to size. Strontium is much bigger than sodium. So this one will be next highest, and this one will be 3rd highest and 4th highest. Somebody, I forget who, had asked me this question. So I am doing it for them. I don't remember who it was. But Eric, if they ask 4 different ionic compound solubility, you will not be able to approach it. So they'll give you different types of compounds that vary in solubility. You guys are welcome, Krina and Akshay. Harshita R. How to solve? The graph below shows the distribution of collision energies of molecule. You also draw another graph with collision energies. Very good. So at 120, if the Maxwell distribution graph is like that, at 120, then 30 degrees, it will become narrower and it will move to the left. If you increase its temperature, it becomes flatter and moves to right. So this is increased temperature. As compared to the one they've given, this is decreased temperature. Okay. Shunali, we will not do, I remove the charged ones. We'll just do molecules that have no charge, okay? All right. Don't worry about the charges, Shunali, okay? We're not going to do that. Isn't it 2 boxes and then 1? Akshay, there are 2 different structures. The first one till nitrogen, I think 2 at the bottom and 1 on top. And from oxygen and fluorine, it flips. And I'm very tired right now. I've been going nonstop. So I might have flipped them, but that I'm pretty sure till nitrogen, there are 2 at the bottom and 1 on top. But yes, between nitrogen and oxygen and fluorine, the structure is flipped around. But it'll be given to you, so you don't need to worry about it or memorize. Stravia. All right. That sounds about time. It's 8:40, guys. Are there any last-minute questions? What kind of Maxwell-Boltzmann question? Is it really a learning objective in this one? I don't remember. I don't have it in front of me. If it is not a learning objective in this, oh, this is the test. Yeah, I mean, so then definitely this is part of the learning objective, Alan. And what kind of questions? On Maxwell-Boltzmann question, there is energy distribution. They can ask what will happen to kinetic energy and temperature changes. They can ask you to draw a graph when the temperature is increased or decreased. So those kind of questions. You don't get mathematical questions on Maxwell-Boltzmann distribution, but you do get graph-based questions. Catherine, yes, pi bonds will always restrict rotation. Bond is not movable around pi bond. Shravya, do we have answers to the epichemistry problems in the review? Yeah, I have all of the answers in the packet, and I think the key was posted also. And if it is from College Board, if it is an AP question, you can always Google the question and you will find the answer online. So either it'll be in the key, in the classroom, or in the key that I posted. Also, guys, your quiz 5 retakes have been graded. I will be at school like half an hour before class starts. So if you wanted to look over your Unit 5 retakes, you are welcome to do that. And I will put it on Facebook group as well. So just know that. Any other questions, elements? Otherwise, I'm getting very tired now. I hope you guys will get a good night's sleep. Believe in your preparation. You have worked towards it. You will be fine. Can we look over retakes during tutorial? Yes, you can, Alan. I really try to minimize the time. So please try and come little before school so you can do it then. But yes, you can do it at tutorial as well. Are the AP questions on Facebook? What does that mean, Harshita? I am not sure what you're asking. Oh, AP questions, College Board questions are on College Board site. You can just go to, let me type it. AP Chemistry FRQ. It's called AP Central. Here you go. You guys are so welcome. One more question, Akshay. Last question. With the sigma and pi bond, how come you didn't count OH bonds? I'm sure I did, unless I messed up. So let's say it is CH3OH. If I drew structure like that, Akshay, you would know that this oxygen octet is not complete. It only has 1, 2, 3, 4. So you need 5, 6, 7, 8. You must draw that. So now when I'm counting sigma bonds, they are 1, 2, 3, 4, 5 sigma, no pi. But if I have CH3COOH, again, you must complete the octet before you start counting. Well, it doesn't so much matter for sigma and pi, but it matters for hybridization or for geometries. So 1, 2, 3, 4, 5, 6, 7 sigma and 1 pi bond. Alrighty, elements. Now my brain's going to shut down. I'm going to stop working. Okay. Good night, elements. I will see you bright and early tomorrow. Okay. I'm going to end the stream now. Good night, everybody. Bye-bye. You guys are so welcome. Thank you. Bye.